Hi everybody, welcome to Test 2 review in Calculus 3. As always, we have the topics of the question on the top. And the first one on the list is equation of a plane. So equation of a plane is a x minus x naught, b y minus y naught, and c z minus z naught equal to 0. Where we have a, b, c here is a normal vector. So we need a vector normal to or orthogonal to a plane, and then we have to have a point, any point on the plane. So we need a point and a normal vector, then we have the equation. Alright, so the first one is straightforward. We have the normal vector, we have a point. So we're just going to use that formula. So it is going to be 4 times x minus negative 6 plus 3 y minus negative 2 plus 3 z minus negative 5. So we have a point and the normal vector 4, 3, and 3. That's the normal vector equal to 0. So we're going to have 4 x plus 6 plus 3 y plus 2 plus 3 z plus 5 equal to 0. We can multiply it out. 4x 24, 3y and 6, 3z and 15. And now if we keep x, y, z on one side, move the constant to the other side, we will have 4x plus 3y plus 3z and 24, 6, that's 30, 15 is 45. Move to the other side, that is negative 45. And that is the equation of a plane. So very straightforward. We need a normal vector and we need a point. A normal vector is orthogonal to the plane. A point could be any point on the plane, and that is the equation. Alright, on the next one, we are not given a normal vector. We have the 3 points though. So the idea is we are given 3 points, P, Q, and R. If we have PQ and then PR, when we do the cross product, we're going to have the normal vector orthogonal to the plane. And this vector could either pointing up or pointing down. As long as it is orthogonal to a plane, it is fine. So we can do PQ cross PR or PR cross PQ. It doesn't matter. Alright, this problem is a little long for that space, so I try to write smaller. So first, PQ. A vector PQ is final minus initial. So Q minus P. Alright. I'm just going to use a calculator here. We don't have to, but it's kind of don't have much space here. I'm just going to put that here for a moment. Alright, so PQ is Q minus P. So pretty much we take the point Q. If we use the vector, we use second parentheses negative 3, 7, and comma negative 50. Close the curly bracket. And that is the first point or the first vector Q. Subtract the point P, open parentheses, second parentheses 5 comma 2 comma negative 50 close. Right, so we have negative 8 negative, just going to write negative 8 5 and 0. Right, so that is PQ. Now we have PR is R minus P. So we have the point P there already. All we need to just go up there, copy and paste. Now just type the point R. Negative 1, 5, and negative 44. That gives us the vector PR negative 6, 3, and 6. Negative 6, 3, and 6. So we found the vectors. Now we do the cross product of PQ cross PR. Or PR cross PQ doesn't really matter. Just take two vectors on the plane and cross them. Right, PQ, the first one, negative 8, 5, and 0, negative 6, 3, and 6. So we cover the row and the column containing I, J, and K. Just going to do that. The first one is 5, 0, 3, and 6. And then negative A, 0, negative 6, and 6. And then negative A5, negative 6 and 3. Of course, in the K component. Right. So cross product we should have that 30 I negative 48 minus 0 or plus 0 negative 48, and then with an extra negative that have 48 J, and then K negative 24 negative 24 plus 30 minus 24, so that's just 6 positive 6K. So we take any two vectors and we do on the plane and we do the cross product. That's what we have. So this is going to be equal to the normal vector. We can use any point. I'm going to use the point P here. So equation of a tangent, equation of a plane is that. Alright, just copy that again. So 30 x minus x naught, x minus 5 plus 48 y minus 2 minus plus 6 z minus 50, so z plus 50 equal to 0. Right. Notice that 30, 48, and 6, all of them divisible by 6. So if we divide everything by 6, we will have 5 x minus 5 a y minus 2 and 6 divided by 6, so that's 1 z plus 50. I would multiply it out. 5x minus 25 ay minus 16 plus 50 equal to 0 plus z plus 50, sorry. Right. So we have 5x and ay and then z. The numbers negative 25, negative 16, that negative 41 plus 50 is negative 9. I mean, negative 41 plus 50 is positive 9. And then move to the other side, so that is negative 9. Right. On the test, we can just stop at this equation. That is good enough already. Multiply it out, because sometimes if you pick two other vectors, we might have a negative vectors or a longer vector. Regardless, any two vector, when we do the cross product, we should have the normal vector. It could be a little longer, a little shorter, or pointing in the opposite direction, but it doesn't matter. Right. So that's what we have in the equation of a plane. On the quadratic surface, 3, 2, 6, we did those problems in class, so we're not going to do that again. Next, we go to the domain and range of a function of multivariable. Right. Actually, we don't have that question on this, so I'm going to just check it out. Now, the level curves for the function. Right, the level curve or the level surface for higher dimension. We're going to take the function, the dependent variable. We're going to choose that to be some constant. By the way, the square root cannot be negative, so we will not choose any negative number for z. Let's choose some values for z. So let's z equal to 1, I mean 0. We have 0 equal to square root of x squared plus y squared. I will square both sides. Now, x squared is greater than or equal to 0, y squared is greater than or equal to 0. When we add them, greater than or equal to 0. So it can only be equal. So the only point that's satisfied here is 0, 0. Or we could consider that this is the equation of the circle, but the radius is equal to 0. So at 0, we just have one point. Right, next. Let's z equal to 1. So we have 1 equal to square root of x squared plus y squared. Square both sides. And this is a unit circle. Center, of course, at 0, 0. And the radius is 1. So when z equal to 1, we have a circle. Radius 1. So it's like that. And then next, let's z equal to 2. We have 2 equal to square root of x squared plus y squared. Square both sides. And this is a circle. Radius equal to 2. And then we just keep doing that. Z equal to 3 and higher. So we have concentric circles. Now we have the limits. So the limit, the first rule of the limit, of course, we're just going to put the numbers where x and y approach until we're just going to put that into it. If we have a number that is defined, that will be the limit. So if I put it in 0, we have 7 0 square plus 10 times 0 square plus 5 all over 7 times 0 square minus 10 times 0 square plus 9. So that is 5 over 9. Notice I did not write the equal sign here. Just put in the numbers. If this is a well-defined number, then we will make them equal to. And that's all we do. Right. So that is when we find the limit, if we put in the numbers, and that works. Now what if it doesn't work? So we look at this equation, this function and this function. So in this case, let's read the instruction first. So that the function has no limit, and we have two paths approaching to the point. So we have two different paths that show the function has no limit. So this should be simple. Usually we're going to choose x equal to 0, y equal to 0, y equal to x, y equal to negative x, or y equal to x squared, y equal to negative x squared. So pretty much we're going to can choose y equal to x to raise to any power. We can multiply 2 or 3, it doesn't matter. Plus or minus. The point is when x go to 0, then obviously y go to 0. We can also choose y equal to sine x, because sine of 0, sine x go to 0 as x go to 0. We cannot choose cosine, because when x go to 0, cosine equal to 1. So because both of them approach 0, 0, we cannot just choose anything. We cannot say y equal to cosine of x, because x go to 0, y is not. We need to choose some function that when x go to 0, y will go to 0 as well, and vice versa. Alright. So the first one, I just try with x equal to 0, see what happens. So first, we do that along the line x equal to 0, which is the y-axis. With that, the limit of the function because x is equal to 0, x already equal to 0, so we need to write is only y go to 0 here, because x already 0. So we know x is equal to 0. That means we just have y squared like that, and y squared cancel out. We have limit of y go to 0 of 1, which is equal to 1. Alright, so that is one path along the y equal to x. Now we do another path. The answer may not be unique. You can just choose any two paths that have different limit. Now choose y equal to 0. Take the limit where x, y go to 0, 0. Now since y equal to 0, we only need x goes to 0. because y already 0. So we have y is equal to 0. So this is equal to limit of x goes to 0 of 0 over negative x. 0 divided by anything is 0. So this is equal to 0. Now we just shows that the limit along the x-axis, the y-axis equal to 1, limit along the x-axis equal to 0, and these numbers are not the same. Because of that, the limit does not exist. So that's what we show. That's what we need to show. Two different paths give us two different limits. Alright, next, number 10, we'll do the same thing. First, we'll do it along the x-axis or the y-axis. So let's choose x equal to 0. So the limit of the function where x, y go to 0, 0. Now since x equal to 0, we only need y go to 0. Because x already is 0. So x is equal to 0. So that's 0 divided by y squared, which is 0. Limit of 0 is 0. Right, and then of course we choose different path. If we choose y equal to 0, this should be the same, because if we put 0 on the top, it is going to be 0 over something else. So it's not going to work if we choose 0. So in that case, we have to choose something else. And it could be, how about y equal to x or y equal to negative x. It doesn't really matter. So we said, let's do that along the line y equal to x. In which case, the limit now since y equal to x, we only need let's say y equal to x, so we write everything in terms of x. So we're going to say x, we only need x equal to 0 goes to 0, because y equal to x, y will go to 0 as well. So we only need one of them. We can say x equal to y here. Right. Now y equal to x, so we have x squared plus x squared, and simplify this, we have limit when x goes to 0 of x squared over 2x squared, which is 1/2. Now we have along two different paths, the limit different, and that's what we need to show. So this is the result. We have different values here. So different limit on two different paths, the limit does not exist. And that's what we do. Again, we're going to choose y equal to 0, x equal to 0, y equal to x, y equal to negative x, or y equal to any power of x, or x equal to any power of y. But one of them go to 0, the other must go to 0 as well. We cannot choose this function. We cannot say y equal to x squared plus 1, because x go to 0, y is not. Right. So that's what we have. Oops. Next, partial derivatives. Right. Number 11 is too easy. I'm not going to do that. Just number 12 here. So derivative, partial derivative, because with respect to x, with respect to y. So derivative with respect to x, we have ln of something. So I'm going to put this. Derivative of ln is going to be equal to 1 over that box, and then we take derivative of that box with respect to x. By the way, this is the long way to do it. So y to the 9, x to the 7. Right. Divide by fraction is multiply reciprocal, so I'm going to flip that. That's what we have. And now derivative of this with respect to x. X to the 7, meaning x to the negative. Divide by x to the 7 if we move to the top. Now just write this part along is equal to x to the negative 7, y to the 9. And when we take derivative of that, it is negative 7 x to the negative 8, and then y to the 9. Cancel. And x to 7, x to negative 8, we have negative 7 x to negative 1. Right? Next, f of y. Again, this is the chain rule. Derivative of ln of something is going to be 1 over that thing, and then derivative with respect to y. Doesn't matter what inside the parentheses is. Now in the parentheses we have y to the 9 and x to the 7. Which we write like that. Right. Divide by fraction is multiply reciprocal. And then derivative of that with respect to y is going to be 9 x to negative 7, y to the 8. X to the negative 7, x to the 7 cancel out. And we have 9 y to the 8, which cancel out. Y to the 9, y to the 8, we have 9 over y, or 9 y to the negative 1. Right, so that is the long way to do it. Right, the best way to do this is using advantage of the properties of the ln, or the natural log. First of all, we have a division here, which turn into a subtract, a difference. By the way, this is one way to do it. This is different way. I should say the alternative solution. Right. So the properties of the natural log or any log, log of division is difference of the logs. Right. Next, we can also take the exponent outside as a coefficient. And then with that, derivative would be extremely easy. Derivative with respect to x then that y would be a constant. So we just need to take derivative of this. Because y is a constant, derivative of a constant is 0. So that is just negative 7, 1 over x for ln of x. So negative 7 x to negative 1. And now derivative with respect to y, so x is constant. So we just take derivative of that, which is 9 times 1 over y. Or 9y to the negative 1. Yeah. So if we use the properties of the log, we rewrite a function, derivative will be a lot easier to do. Right. So the rules of partial derivative. With respect to x, we will treat y as a constant. With respect to y, we're going to treat x as a constant. Right, now we go to 13. Right, 13. Derivative with respect to x. Alright, this one have an x there. Derivative of x squared is going to be 2x. And then y is a constant, will stay there. Next, derivative of this with respect to x, there's no x there, so y squared plus z, this is constant. Derivative of constant is going to be 0. Constant with respect to x, so that's going to be 0. Derivative of this of x is going to be 1, and derivative of z, z squared is a constant with respect to x, so stay there. So we just take derivative with respect to x. The other variables are constant. So that's what we have. So that is 2xy plus z squared. Right, next, derivative with respect to y. Now the first one we have y here. X squared is a constant, doesn't do much. Derivative of y is 1. Derivative of y squared is 2y. Z is a constant, we stay there. So we have x squared plus 2yz. And derivative with respect to z, that one is constant. With respect to z, so we have y squared, that constant. Derivative of z is 1. And then x is a constant. Derivative of z squared is 2z. So we have y squared plus 2xz. Right, so that is the partial derivatives. If it is derivative with respect to x, we're going to treat y as a constant. If it is with respect to y, we're going to treat x as a constant. Every other variable will be treated as a constant. Oops, wrong one. Right. Next we have the chain rule. So in order to do the chain rule, we have to see the structure of the function. So first of all, we have w is a function of x and y. So we're going to write w here is a function of x and y. And then x equal to cosine t, y equal to sine t. So x is a function of t and y is a function of t. So when we write the chain rule of w with respect to t, meaning that we go from w to t, or from t to w, we're going to have two possible paths. W to x, x to t, w to y, y to t. So the chain rule, the formula for the chain rule here, w over dw over dt is going to be from w to x, meaning dw dx. Notice that because w is a function of two variables, so that actually the partial derivative. X is only the function of only t, so that's going to be dx over dt. Next, w to y, still partial derivatives, and then y to t. Alright. Now we just take the derivatives. Derivative of w with respect to x. So that will be 2x minus 6. With respect to x. Derivative of x with respect to t is negative sine t. Derivative of w with respect to y, that will be negative 2y. And derivative of y with respect to t, that will be cosine of t. So that is the formula for the chain rule. Now we need the values. T equal to 3 pi. So if we put 3 pi in here for t, cosine of 3 pi, cosine of 3 pi is like cosine of a pi, which is negative 1. And then, so x is equal to negative 1. Just write x equal to negative 1. And y equal to sine t, sine of 3 pi is like sine of a pi, which is equal to 0. So y equal to 0. And t equal to 3 pi. Right. And we're going to put t equal to 3 pi, x equal to negative 1, y equal to 0 into this. So 2 times x times negative sine of 3t minus 2y, plus negative 2, y we know is going to be 0, and then cosine of 3 pi. Right. Well, sine of 3t, that is 0, so that's 1 0, and negative 2 times 0, that is also 0, so 0 and 0, so that is going to be equal to just 0. Right. So we need to know the map of this. Next, we find the derivative of w with respect to u. Want to draw the map. The function w has two variables, x and y, and each x and y, x is a function of, they have two variables u and v here. Now we want the derivative of w over du, meaning we go from w to u, and that will be this path. That is 1. And this is another path from w to u. So we're going to write again derivative, then either w, u, or v, so we still will use partial here because there are more than one variable. Right, w to x, w have two functions, have two variables, so it is going to be partial derivative with dx. And then from x to u, also two variables. And then dw with respect to y, and dy partial y with respect to u. Right. Now just do the partial derivatives. of w with respect to x, that will be just y, of x with respect to u will be just 1, of w with respect to y, so that will be x minus 2y, and derivative of y with respect to u, that will be just v. Right, now the values. We know u and v is 4 and 2. So now we're going to solve for x and y. X is equal to u minus v. U is 4 minus v. So x is 2. Y is equal to u times v. 4 times 2, 8. So x is 2 and y is 8. And then we substitute back into the problem. Y 8 plus x 2 minus 2 times 8 times v. V is 2. So we have 8. 2 minus 16, so that's minus 14 times 2, minus 28 plus 8 minus 20. So in the chain rule we need to write draw the map and to see where do we go from the top dependent variable to a independent variable and the sum of all the possible paths. So there are 2 paths here from w to u this way and the other way. So there will be 2 of them. Alright, so that is the chain rule. Next, we have implicit differentiation. Right. So we have something like this, similar to this in calculus 1, a little more complicated. Here it will be a lot easier. dy over dx is equal to negative f of x over f of y. Alright, first of all, what is the function f? Well, that is the implicit function, so that is f of xy equal to 0. So we need a function that is equal to 0. And then in that case, it is equal to negative partial derivative with respect to x over partial derivative with respect to y. Notice that there is the negative sign and dy over dx. This is f of derivative with respect to x over partial derivative with respect to y. Right. So first, the function is 3x squared 5y cubed plus 7xy. Then we take derivative with respect to x. Partial derivative with respect to x, that will be 6x. X will be 7 times y, 6x plus 7y. And derivative with respect to y, that one is a constant. This gives us 15y squared. And y, we treat x as a constant, so we have 7x. Derivative of y is 1. So just that. And then we're going to put in the formula here. Derivative with respect to x. 6x plus 7y. So derivative with respect to x, and partial derivative with respect to x, and then partial derivative with respect to y, 15y squared plus 7x. We evaluate at 1 and 1, at x equal to 1, y equal to 1, so we will have equal to negative, now equal to 1, that will be easy, 1 and 1, so we have 13 on the top and 22 at the bottom, and that's what we have. So that is implicit differentiation. If we have the function of 3 variables, let's say if we have the function of 3 variables, and then we want to find derivative of y with respect to x, for instance, x actually have to be, in this case, so we're going to do negative f of x over f of y. Pretty much the same formula, but this time because there are 3 variables, so it's not dy over dx, it is partial derivative of y with respect to x. So that is where we have 3 variables. So that implicit differentiation 16. Next we have the gradient. That will be 18, and then directional derivatives will be 17. Right, so we're going to do those two together. First, the gradient. So the gradient is just it's denoted by del f. Somebody used to write this as a boldface. Just denote that this is a vector and not a function. It doesn't matter. I'm going to just use the regular upside down triangle f we call del f. Right. In general, it's just the vector of partial derivative. Here we have 2 variables, so 2 partial derivatives. So that is easy. And after that, we evaluate at the point. So we're going to have the point. So first, partial derivative. So del f equal to derivative with respect to x, negative 18x and negative 7. And then we have to evaluate at 9 and 10. At xy equal to 9 and 10. So here we have the gradient at the point 9 and 10. So I'm going to put 9 in for x. And that's it. There's no y to substitute in. 18 times 9, so like 18 times 10 minus 18, so 180 minus 18, that's 162. Right, so the gradient is the vector of partial derivatives. So we just write like that. So that's the gradient. Directional derivative is not a vector, even though it said directional derivative. So directional derivative in direction of the unit vector u of the function f is equal to the gradient will be at the point the function at that point or some point dot with the unit vector. It has to be the unit vector. This vector given here is not unique. It's not unit. So we have to turn that into the unit vector. We check the vector divided by the magnitude. So we have the vector of 3, 6, -6, and -2 divided by the magnitude. 6 square, -6 square, 36, 36, 72. Oh, sorry, that was 3, right? So this should be 3. And then -2 square. Right. 3 square is 9, 36, 45, and 4, 49. So that is 7. So 3, -6 over -2 over 7. So the unit vector u is 3 over 7, -6 over 7, and -2 over 7. Next we're going to take find the gradient, evaluate at the point, and then dot with the unit vector. Right, first we find the gradient. Let me just write. This is the vector u, the unit vector u. Give us the direction. And now we find the gradient. Partial derivative of the function -3, 10, and 8. Right. We don't really need to put in the point because there's no x, y, z here. So we're going to take that vector for the gradient. Evaluate at the point, which we don't have x, y, z here, and then dot that with vector u. Alright, so that gives us -3, -3, that's -9 over 7, 10 and 60, -60 over 7, and -16 over 7. -9, 16, 25, 60 is 85. Notice that directional derivative is just a number. It has no direction because of the dot product. So we find the gradient at the point, and whatever the direction is, it has to be in terms of a unit vector. So we just do the dot product, and that's what we have. So gradient is 18. Directional derivative is 17. Next we have equation for tangent plane and linear approximation. These two equations actually is the same. So 19 and 20. So equation of a tangent plane and linear approximation will be the same because we use the tangent plane to approximate the values of a curve, which is the function. So the idea is just like in calculus 1, if we have a curve and a tangent line, so to estimate the values of the curve, we just use the line to estimate. Generate that into higher dimension. We're going to use the plane to approximate a surface. So we increase that to 2 dimensions, and the line becomes a plane, and a curve becomes a surface. Anyway, I'll show the equation. Equation of a tangent plane, z equal to the values of the function at point A and B plus derivative with respect to x at A and B times x minus A plus derivative with respect to y at A and B, y minus B. Right, now we have the function like that. The point is here, meaning that A is 2, B is 1, and the values of the function is 37. Right, so that means we have this is 37. If it's not given, then we have to put 2 in for x and 1 for y here, and to find the values. But it's there already. The point A here is 2, B is 1. We need to find the partial derivative with respect to x and partial derivative with respect to y. Those two will be determined. X and y, the variable, will stay there. Right. So we have the function z is that, or we can say f of xy equal to instead of z. So if we take the derivative with respect to x, derivative of this with respect to x is a times 2, so it will be 16x. And we evaluate at 2 and 1. When x equal to 2, so derivative of with respect to x at 2 and 1 is equal to 2. Here should be 16 times 2, 32. And then we find derivative with respect to y will be 10y for that function. Axy is a constant, and we evaluate at 2 and 1. X equal to 2, y equal to 1, so derivative with respect to y at 2 and 1 is 10. So we find out that this is 32 and this is 10. So the equation becomes z equal to 37 plus 32 x minus 2 plus 10 y minus 1. We can leave it like this, or we multiply everything out and keep x, y, z on one side. I will do that. We have z 37 32x minus 64 10y minus 10. Right. Let's just move the z to this side. So we have 32x plus 10y minus z. Move z to that side. And then the numbers 64, 74 minus 37. So that is negative 37. You can say just plus 37 equal to 0. Move everything on one side. That's what we have. Or we move the 37 to the other side. Wait. Negative 64. So that should be negative. Right. So we move everything on one side, the right hand side. That's what we have. Or we can move the 37 to the other side. Or we write 32x plus 10y minus z equal to 37. Negative 37 move to the other side, becomes positive. So that is the equation of a tangent plane. Will be that. So linear approximation will pretty much the same formula. I'm going to write that out again. Right. First of all, this is A, this is B. The function and when at 0, 0 we have the function at 0, 0 e to the negative 6 times 0 plus 7 times 0 e to the 0 power is 1. So we have the values of the function is 1. This A is 0, this B is also 0. We just need the partial derivative with respect to x and with respect to y. Derivative with respect to x. Now it will be easier if we rewrite the function as e to the negative 6x, e to the 7y. When we write like this, this is with respect to x, that one with respect to y. Derivative will be very easy. Now with respect to x, e to 7y is a constant, so it will stay there. So we have negative 6 e to the negative 6x. That is derivative with respect to x of that one. And then we stick a constant to it. Zero power is 1, so this is negative 6. Derivative with respect to y. Minus 6 x minus 0 plus 7 y minus 0, which means z equal to 1 minus 6x plus 7y. So that is a linear approximation of the function. Now if we have a point close to 0 and 0, for example, if we have x equal to 0.01 and y equal to negative 0.1, put in here we have the values of the function. For example, if we want to evaluate what is the values of the function at 0.1, negative 0.2, for instance, if the numbers here are close to 0 and 0, instead of putting this function, we can just put in this equation of a plane, and that gives us a better, approximation of the values of the function. Right, so that's what we have. So equation of the plane, that will be tangent plane, that is 19. And linear approximation, that is 20. Now we go to the second derivative test. First, this is probably a little bit long, so just cut the page in half. Try to write a little smaller. Right. So we're trying to find relative extrema, relative maximum, relative minimum, or the local max or local min. Could be shadow point. And we use the second derivative test, and I have to use that. So first, have to find the critical points. Critical points meaning all the partial derivative equal to 0 or do not exist. We just focus on the case equal to 0. Is equal to 0 or do not exist. Derivative with respect to y equal to 0 or do not exist. The function is resembling polynomial, so it is defined everywhere. So we don't have to worry about the case where they do not exist. Right, take derivative with respect to x. Give us 3x squared and minus 12y, and derivative with respect to y, negative 12x plus 24y squared right, and we're going to solve this equal to 0. Let them equal to 0, and we solve the system of equation. I'm going to rewrite that here. 3x squared minus 12y equal to 0, negative 12x plus 24y squared equal to 0. This is a nonlinear equation. We cannot use the calculator find reduced row echelon form. It's not going to work like that. So we have to go back and back to algebra, either elimination or the substitution. I will go with elimination here. So let's eliminate x and then solve for y, or eliminate y and solve for x. Either case. If I want to eliminate y, I try to make this the same. So I will multiply the top equation by 2y. In that case, that will give us negative 24y squared, which cancel. The second equation I'll keep the same. So do that, we will have the system of 3x, 6x squared y minus 24y squared equal to 0. And then negative 6, negative 12x plus 24y squared equal to 0. Now if we add side by side, those two cancel out. We have 6x squared y minus 12x equal to 0. Right. Now, let's write this 6x squared y minus 12x is equal to 0. We can factor out the 6x. Notice we can only factor, we cannot divide. And that gives us xy minus 12 minus 2. Right? Factor out 6x. We have xy left minus 2. So a factor equal to 0. So this gives us 6x is 0, or xy is equal to 0. So product equal to 0, one of the factor must be 0. So we have x equal to 0, and here if we solve for x or solve for y, we have y equal to 2 over x. So there are two scenarios there. So when x equal to 0, I'm going to substitute into, let's substitute into this equation. I mean, this is, yeah, that equation. Put 0 in for x, we have negative 12y. I just say 3 times 0 square minus 12y equal to 0. So that gives us negative 12y equal to 0, or y is equal to 0. Now what happens when y equal to 2 over x? I'm going to substitute in here. We have 3x squared minus 12y is 2 over x. That gives us 3x squared minus 24 over x equal to 0. I will multiply everything by x. We have 3x cubed minus 24 equal to 0. Divide both sides by 3. X cubed is equal to 8. Take the cube root on both sides. X equal to 2. Now since x is equal to 2, y is equal to 2 over x. Two over 2 is equal to 1. So bottom line is when x equal to 0, y equal to 0. So we have critical point. Xy equal to 0, 0, or x equal to 2, y equal to 1. Right, so two critical points there. Right, so that's the first part of it. Partial derivatives equal to 0 and solve the system of equation. Right. Now the second part is determine if they are derivative, if it is maximum or minimum. So the second step is second derivative test. Second derivative test. Which we need the second derivative, obviously. So derivative with respect to x is that when we take the second derivative with respect to x, we will have 6x just that. Derivative with respect to x, y. So derivative of this with respect to y is negative 12. And derivative with respect to y and then y will be 48y. Right. Second derivative test. Let's go over the rule first. So first we're going to find the discriminant fxx, fxy, fyy minus fxy squared. If we happen to forgot, it's actually from the Hessian matrix fxx, fxy, fyx, fyy, and then 2 by 2 determinant, multiply and then subtract. That's what we have here. So that is the discriminant. If the discriminant is positive, then there we have a max or min. If the discriminant is negative, that is the saddle. And d equal to 0 is inconclusive. Right. For maximum, of course, if the function open up, it is the minimum. If open down, it is the maximum, meaning that the second derivative with respect to x have to be negative. Minimum is where it open up, so f of xx is positive. So that's what we have. So find discriminant and then positive, we have max or min, negative is a shadow. Right, we'll get back to this. Right, discriminant fxx fyy minus fxy squared. So we have fxx 6x times 48y minus negative 12 squared right. So d is equal to 6 times 48. I have a calculator here. 6 times 48, 288 xy plus 144. Sorry, minus 144. Right. So that is the discriminant. Now we'll have 2 points. First at 0, 0. We're going to put 0 in 0 for x and y. That is less than 0. If it is less than 0, it is a saddle point. So 0, 0 is a saddle point. Saddle point. If the discriminant is negative. And now we go to x equal to 2, y equal to 1. We're going to put 2 in for x and 1 in for y. Right, so that looks like positive. Now if it's positive, it is either max or min. We don't know yet, so let's say max or min. So we have to do one more thing. In that case, what is the partial derivative with respect to x? 6x, 6 times x is equal to 2. And that is positive. Positive meaning it open up. If it open up, it is going to be a local mean. So we have a shadow point at 0, 0 and a local mean at 2 and 1. Right. Also, we can do the same thing on 22. Again, partial derivative equal to 0, usually elimination or substitution. Here we have elimination. And actually we do have some substitution too. So after we find the critical points, we go to the second derivative test. Second derivative test, we have to find all the second derivative and the discriminant. Discriminant, which is the determinant of the Hessian matrix. So we do that. Discriminant positive have either max or min, negative a shadow point equal to 0, inconclusive. Now to determine max or min, we have to look at the partial derivative fxx. If it's less than 0, it opens down and the max. If it's greater than 0, it's open up and that's the mean. Right. I'll let you do number 22. To practice. last topic is Lagrange multipliers. Will be those two. Right. 23 actually easier and a little bit easier than 24. Right. So Lagrange multipliers. So first, in Lagrange multipliers, we have to write the function and the constraint. The constraint can be equal to a constant, but in the book they use 0. So I'll roll this around, and we say x squared plus y squared minus 1 equal to 0. And we let that be the constraint function. Right. So move everything on one side, make that equal to 0, and that is the function g of xy. Right. Now the method of Lagrange multipliers. This is also a long problem, so I will divide the page in two. So we will take the gradient of the function is going to be the multipliers times the gradient of the function g, and then we have the function itself equal to 0. Right. So that system of equation actually we can write as the partial derivative with respect to x. I mean for the top two here, for this part, we can write as derivative with respect to x equal to derivative with respect to x of g, with respect to y, lambda g of y. In class I will write the alternative form for it, but you can just use that. So derivative with respect to x of the function f is 14x equal to lambda times derivative of this with respect to x is 2x. Derivative of the function y f with respect to y is 10y, and then because this. So instead of write like that, we can write the system of three equations like this. So this is f, this is g. Take derivative with respect to x and make them multiple of each other. Take derivative with respect to y and make them multiple of each other. 2y. And then the constraint itself. Alright. Once again, we do not have linear equation. The bottom equation, we can write x squared plus y equal to 1. Right. Here we can do the use elimination or substitution. Right. The objective here is, notice the lambda is the Lagrange multipliers. We really don't need to know what it is. The objective here is to find out the point x and y. So if somehow we can eliminate lambda, that is good. Alright, so I'm going to eliminate lambda because we don't need lambda. So to eliminate lambda, I multiply the top equation here by -1 and just keep the second, each second equation multiplied by x. Right, let's write that again. 14x equal to 2 lambda x, 10y 2 lambda y x squared plus y squared equal to 1. Right. Multiplying by negative 1 and I multiply by x. Sorry, negative 1 times y and then multiply by x. So in that case, both of them have 2 lambda xy, but the top is negative, the bottom is negative. So that's good. So multiply by negative y, we have negative 14 xy equal to negative 2 lambda x y. This multiplied by x, 10 xy equal to 2 lambda xy. Right, so that's good. We add side by side, negative 4 xy equal to 0. Right, so that turned out to be very nice. We just have negative 4 xy equal to 0 and then x squared plus y squared equal to 1. Right, so we eliminate lambda and that's what we have. Next, from this equation, a product equal to 0, I just divide x and y both sides. Divide by negative 4, cannot divide by x or y. So we just have xy equal to 0. Now if xy equal to 0, we have either x is equal to 0 or y is equal to 0. Right? So divide by negative 4 on both sides. X times y is equal to 0. A product is equal to 0. At least one of the factor is 0. So we're going to write at x equal to 0, we're going to substitute into x squared plus y squared equal to 0. If x is equal to 0, y squared is 1, so y is equal to plus or minus 1. So from here we have 2 points, x equal to 0, y equal to 1, and x equal to 0, y equal to negative 1. Notice a square equal to a number where we take the square root on both sides. Don't forget the plus or minus. Then when y equal to 0, I'm going to put 0 in for y. X squared equal to 1, so x equal to plus or minus 1. So our solution is 1, 0 or negative 1, 0. So there are 4 points. So we find the points. The rest is simple. Just trying to find which one is the max, which one is the min. So that part is easy. We have the function 7x squared plus 5y squared and then evaluate at the point. Alright. Next, let's just make a little table. Right. X 0 and 1, 0, negative 1, 1 and 0, negative 1, 0. Of course, this is very easy. But if you want to use a calculator, it's just a demonstration. We can use a calculator here. Put that. So I will go to list. So I hit stat, edit, hit enter. Enter. Right. 0, 0, 1, negative 1, 0, 0, 1. The numbers are very easy. We can do that by hand. But I want to show using the calculator because when the number get more complicated, this will come in handy. Alright. So we put those for x, those for y into list 1 and list 2. and then we go to list 3. It's very important here that we have to highlight the list 3. Highlight the list 3. We're going to enter 7x squared plus 5y squared. 7. We cannot really enter x because x is L1. So we hit L1. Second, number 1. So that's 7L1 squared or 7x squared plus 5. Second, number 2. And we have 5577. So obviously this will give us the mean and this gives us the max. So we say this is actually the absolute maximum, absolute mean, or we just say the minimum equal to 5 at 0 and 1 or 0 and -1. Max equal to 7 at -1, 0 or 1, 0. Sorry, let me put the calculator away. Right, so that we have Lagrange multipliers. Yeah, so sometimes we try to, the point here is we try to eliminate lambda. In that case, we don't have to deal with lambda because as you see, it's irrelevant. We don't really need to know what is lambda. All right. There's another way to do this is we show everything in terms of lambda. This will be complicated in this one. Right. So I think I'll go to 24 also. Right, 24. The same Lagrange multipliers. First, I need to write g of xy is equal to x squared plus 2y squared minus 6 equal to 0. Right, also long problem. Let's divide the pair in half. Right, so we have the system equation. Take the derivative of f and the derivative of g, both with respect to x, and let them be multiple of each other. So this derivative with respect to x, and let's just write that out. Derivative with respect to y, multiple of each other, and then the constraint itself. Right. Derivative with respect to x for f is 2xy. Derivative of g with respect to x is 2x. And derivative with respect to y here is x squared, and that will be 4 lambda y. So that with respect to y, and then the constraint itself. I just write that equation. Or I move the 6 to the other side, and we have that equation. It should be the same. Right. For that, I try to eliminate lambda still. So I have to multiply something on the top, something on the middle equation. Right, so we need something common to eliminate. One positive, one negative. Lambda x, lambda y, so why don't we multiply a y here and an x here. And then they need to take care of the numbers as well. So if I multiply by 2y, I will have 4 lambda xy, which is the same as here. Let one of them be negative. Right, how about that? Right. Do that. We will have 2, which is 4 x y squared . equal to 4 lambda x y negative x cubed negative 4 lambda x y. Add side by side. We have that. So we eliminate lambda, and now the system of equation only have two equations for xy squared minus x cubed and x squared plus 2y squared equal to 6. We have no more lambda, which is good because we don't need lambda. We only need x and y. Right, so for this equation, can factor out the x. And then we have 4y squared minus x squared equal to 0. Right? So a product is 0, at least one of them must be 0. So we say x equal to 0 or 4y squared minus x squared equal to 0. This gives us the second part though. X squared equal to 4y squared. Take the square root on both sides. X equal to 2y. But don't forget that we need to have the plus or minus here. So take the square root on both sides, but with the plus or minus. And so x is equal to plus or minus square root of, plus or minus 2y. So three cases here. X equal to 0, x equal to 2y, and x equal to negative 2y. X equal to 0. Let me zoom out because the camera, that is. Right. Now I have the whole problem. Right. At x equal to 0. If x equal to 0, I'm going to put in that equation 0 squared plus 2y squared equal to 6. So y squared is equal to 3. Y is equal to plus or minus square root of 3. So there are 2 points here. 0 square root of 3. 0 negative square root of 3. 2 points. Okay. Now x equal to 2. Put 2 in for x. That is 4 plus 2y squared is 6. So y squared is 2. 2y squared is 2. So y squared is equal to 1. So y is plus or minus 1. So we have the point 2 and 1, 2 and negative 1. And then next, x equal to negative 2. Put negative 2 in for x. We have the same thing. And that gives us y equal to plus or minus 1 as well. So the point is x equal to negative 2, y is 1, x equal to negative 2, y is -1. Right. Almost run out of space. Now we go to a table. Actually, we do run out of space. There will be 6 points. So the function is x squared y. Right. I guess we can zoom back in now. Right. Now the points. 0, square root of 3, 0, negative square of 3, 2 and 1, 2 and -1, -2 and 1, -2 and -1. So all those points. Again, I'm going to use the calculator here. Right. Right. Stat. To hit the stat key and then enter. Right. We need to clear all of the previous data. To clear it, don't ever hit the delete button. That will give on weird things. Just go highlight the L1, hit clear, and that will clear the list. Highlight the L2, hit clear, and that's clear. And then highlight L3, clear, and it's clear. Right. The numbers 0, 0, 2, 2, -2, -2, and square root of 3, square root of 3, sorry, 1 and -1, 1, -1, 1, -1. Right, so put everything there. And then go to L3, have to highlight L3, and then we enter L1 for x, and L1 square for x square, and L2. Right, so we have 0, 0, 4, -4, 4, -4. So we have the maximum equal to 4 at those points. At x equal to 2 and 1, or -2 and 1. And then the mean equal to -4 at 2 and -1, and -2 and -1. Alright, let me zoom out one more time. Of course, the difficult part is how to solve for the points, usually a bunch of points. So to do that, we set up the system of equation. Derivative of f and g with respect to x have to be multiple of each other. And then same thing for y, with respect to y. And then the constraint, the constraint, the third equation. Alright, so we solve that. In this case, usually I try to eliminate lambda because we don't need lambda. When we do that, be careful that we don't divide by x on both sides. If we divide by x, we might lose some solution. So I have x equal to 0, and then substitute back into the equation, into the constraint. We should have the points. When we have the points, we just evaluate at the objective function. The biggest one is the max, the smallest one is the mean, and that how we do a problem of Lagrange multipliers. And with that, we cover everything needed for the second test. I hope it helped you to review for the test. As always, thank you for watching.